All right, good evening and welcome to another installment of Crossroads of Ideas. I'm Leah Hammond and I'm an intellectual property manager at WARF. Is there an echo? All right, Crossroads of Ideas is a collaboration between the Morgridge Institute for Research, the Wisconsin Institute for Discovery, and WARF, and it's an opportunity to foster dialogue between the community and UW-Madison researchers. The series addresses issues that matter to all of us and are also the subject of research at UW-Madison. Before I say more about this evening's event, we'll take a moment to acknowledge the land that we occupy here at the Discovery Building. The University of Wisconsin-Madison occupies ancestral Ho-Chunk land, the place their nation is called Dejope since time immemorial. In an 1832 treaty, the Ho-Chunk were forced to cede this territory. Decades of ethnic cleansing followed when both the federal and state government repeatedly but unsuccessfully sought to forcibly remove the Ho-Chunk from Wisconsin. This history of colonization informs our shared future of collaboration and innovation. Today, UW-Madison respects the inherent sovereignty of the Ho-Chunk Nation, along with the 11 other First Nations of Wisconsin. This evening's session is part of a mini-series produced in partnership with the Office of the Vice Chancellor for Research and Graduate Education, highlighting recipients of WARF's named fellowships at UW-Madison. We're featuring one such recipient from each of the university's 4 divisions. A quick reminder, the next one will be coming up on February 28th, titled, "What Do Americans Think About Foreign Electoral Intervention?" So be on the lookout for that. Before we hear from our speakers, I have a few housekeeping details to review. At about 45 minutes after the hour, we'll go to the audience Q&A. If you're here in the room, please line up at the mic right in the middle. If you are on Zoom, make sure to use the Q&A function to pose your question and not the chat. And we'll make sure to read those aloud during the Q&A and we'll get to as many as we can before concluding the session promptly at 8 p.m. So without further ado, I'm delighted to welcome Associate Vice Chancellor for Research and Graduate Education for the Physical Sciences, Amy Wendt, to say more about the OVCRGE and this evening's speaker.
Thank you so much, Leah, for the introduction, and welcome to all of you who are here live and connected by Zoom. I want to start with just a little bit more about the Crossroads of Ideas series. Crossroads has been a staple of Discovery Connections programming since 2014. This year, we are pleased to highlight the work of several UW faculty who are not only thought leaders in their respective fields, but also honorees of awards sponsored by the Wisconsin Alumni Research Foundation. WARF, along with the UW Office of the Vice Chancellor for Research and Graduate Education, is pleased to collaborate in bringing these faculty to you in hopes that we can all learn more about the ideas and issues driving dialogue in our world today. So again, on behalf of the OVCRGE, welcome to our event this evening. And it is my pleasure to be part of this and to introduce our speaker this evening, Bilge Mutlu, who has been on the faculty of UW-Madison since 2009 and is now the Sheldon B. and Marianne S. Lubar Professor of Computer Science, as well as an affiliate member of both the Psychology and Industrial and Systems Engineering departments. He directs the People and Robots Laboratory and co-directs the Collaborative Robotics Laboratory. His research program focuses on building human-centered methods and principles to enable the design of robotic technologies and their successful integration into the human environment. He teaches undergraduate and graduate courses in human-computer interaction and user experience design on the UW-Madison campus. Dr. Mutlu is the director of the NSF, National Science Foundation, graduate research traineeship program called Integrate, Integrating Robotics into the Future of Work. Dr. Mutlu has an interdisciplinary background that combines design, computer science, and social and cognitive psychology, and a PhD in human-computer interaction from Carnegie Mellon University. He is recognized as a leader in the areas of human-computer interaction and human robotics interaction. He has received multiple awards from UW-Madison, recognizing his research excellence, including the Vilas Associates Award, and in 2022 was the recipient of the WARF-sponsored H.I. Romney's Faculty Fellowship, the highest research honor for his career stage. He has also received the UW's Provost Early Career Award, and he was the co-recipient of the Ellen Newell Award for Research Excellence from Carnegie Mellon University. Dr. Mutlu has received 20 Best Paper Awards and nominations, as well as recognition in international press, including The Economist, New Scientist, and Discovery News. He is the founding chief editor of the HRI section, that's Human Robotics Interaction section of Frontiers in Robotics and AI, and is an associate editor for Human Computer Interaction, as well as Foundations and Trends in Computer Interaction. He co-chaired the Human Robot Interaction Steering Committee and is serving as the Secretary Treasurer of the Human Computer Interaction Consortium. So we're very fortunate to have him at UW and to have him with us tonight to talk about what can robots tell us about our humanity. So before I hand the mic over to our speaker, I just want to say that as an engineer, so I'm an electrical engineer, as an engineer, I have a natural interest in robotics, and as an engineer with an injury, I'm especially attuned to how machines can help me with my life. But I also want to say that this is such a timely moment in today's world, in an era where we have automobiles that can drive autonomously, and we can get instantaneous assistance on any topic from artificial intelligence tools on the internet, such as ChatGPT. So I'm really looking forward to this presentation. And without further ado, Dr. Bilge Mutlu.
Thank you for that great introduction. All right. Well, thank you for being here tonight, especially on Valentine's Day. I decided to open with a Valentine's Day joke. And being the multitasker, I decided to invite my wife so that I would kill two birds with one stone. So with that, I'd like to start to talk about what robots can tell us about our humanity. We look everywhere today and we see robots everywhere. We see physical robots that resemble humans. We see devices that we speak to, and we see artificial intelligence appearing in day-to-day things that we use, from cars to word processors. So what is this about? Why is it that we put so much interest in robots? Why are we so interested in it? We see robots not only in ways that we want to see, but in ways that may not be very productive, but that may still be very human. So in the last 2 decades, I've been working in the area of robotics and studying robots. First at Carnegie Mellon University with a brief time in Japan, and now at this great university. My students and I have looked at how robots should behave around people, and what they should say, how people respond to them, how we can program them, how we can tell them what we want them to do, and how robots can learn from us on our behavior, and also how they should behave toward us. In doing this work, the question that I'm asked most often is, why robots? Why do we make robots, and why do we make them human-like? Why do they have to behave human-like? Why can't we just have intelligent automation just doing things in the background for us and just to benefit us? And why are we instead working on robots that can walk and talk? So what I want to do today is to explore 5 hypotheses for why this might be the case and what that means for us. I'll share evidence and arguments for and against these hypotheses and see what the current evidence suggests, and at the end to see where we stand. And to clarify, these are hypotheses about highly complex socio-technical phenomena. So it's really difficult to test these in a sense. But we'll bring together ideas and data to determine the plausibility of each hypothesis. To start with the first hypothesis that I'll talk about is the affective hypothesis. And this stems from the desire to design robots with human qualities, which means that the robots elicit a human response from people, elicits emotion, and builds rapport and connection with people. After all, that's what we do in art and cultural artifacts. So the hypothesis is that robots elicit emotion. Consider the entire history of human art and cultural artifacts, from ancient statues to food. And the human form and human-like qualities have been used to elicit emotion, whether it's delight, enchantment, or connection. The first example that I want to talk about is an art project from 2011, where the artist built a very simple cardboard robot called Tweenbot that had a smiley face painted on it and a very simple mobile base that can go only forward in a straight line. They put the robot at the entrance of New York's Washington Square Park, and the robot carried a little flag that helped me get to the other end of the park. And the flag that you see there was a deployment in France. And the artist set the robots down and then just sat on a park bench and watched what happened. What happened next was hundreds of people encountering the robot and trying to help it out. People stopping to speak. Let's see. Yep, it's playing. People stopping to speak to the robot. Hey, little buddy, you can't go that way. That's the road. I'm going to put you here, and really care for the robot. Make sure that the robot was going on its way. Its needs were met. And the artist saw this over and over again, over deployments, never saw a single robot being destroyed, damaged, or not reach its destination. And this was very interesting to see because we're looking at this highly incapable robot, very different from the promise that we're seeing with robots, but still evoking a lot of emotion, a lot of, receiving a lot of care and attention and love from people. Another project was a robot developed by 2 media studies professors at Ryerson University that was designed to travel across Canada by hitchhiking. In the summer of 2014, the robot traveled from Halifax to Victoria. It was placed on the side of the road, told the cars where it wanted to go, had the capability to do that, and held basic conversations during the ride. And the robot had such a following, including YouTube channels and Twitter accounts dedicated to following where the robot was, reporting on different experiences. In general, people treated the robot, the Hitchbot, the same way that they treated the Tweenbot. People cared for the robot. They would stop at the side of the robot, understand what the robot needed, which might be strapping it in the passenger seat and plugging in its battery for a charge. The responses were curiosity as well as caring for this lesser being. And unlike the Tweenbot, who was enjoying retirement at the Metropolitan Museum of Art, the Hitchbot was destroyed for its computer parts and left on the side of the road. And of course, that is also very human. Between the 17th and 19th centuries in Japan, a karakuri puppet was used in tea ceremonies. I want to play a little video of that. This was a robot designed to entertain and enchant people during these highly ceremonial events. So they were so successful that they started using them in theater plays as a form of entertainment. And just the experience that a robot delivers you tea, you drink it, place it back, and it takes the empty cup back to where it came from. It's just pure enchantment. And it also reflects Japanese tea ceremonies, because we're not jugging down cups of tea. You're taking a sip and waiting for the next tea. The next robot I'd like to talk about is the reading companion robot that we designed for children called Mini. The children read out to the robot, and the robot helped them set reading goals, commented on the story, connected that story to another story that the child and the robot read together, and so on. We left the robot with children for 2 weeks to see, how their reading habits would change and what they would think about this new reading companion. And there was a control group of a paper-based reading guide, and we wanted to understand how these would compare. Among many findings, the most striking one was that children saw the robot as having personality and emotions much more at the end of the study than they did at the beginning. It really exceeded their expectations of how much they attributed emotion to it and personality to it and build a connection with it. And at the end, they connected with the robot and they were more motivated to read, which reflected in their comments. So with these few examples in mind, let's revisit the affective hypothesis. And I would say that there is generally strong support for this hypothesis that robots elicit emotion, both good and bad. We've seen pity, care, curiosity, affection, sympathy for these robots that we saw. And these emotions manifested themselves in giving the robot help and attention and care, and often affiliating with the robot. The second hypothesis I want to talk about is the mindlessness hypothesis. The concept of mindlessness comes from psychology. It's the opposite of the state of mindfulness. Mindless behavior happens when cues from the environment trigger various existing scripts, labels, or expectations that we prematurely commit to. So we see something that resembles human, and we mindlessly treat it as if it's a human. One place where this mindless responses occur is media. Reeves and Nass, in their 1996 book, The Media Equation, proposed that people treat media, including computers, TV, and new media, which includes robots, as real people. And the quote that you see there is the byline of their book. So this equation is so strong that if the cues are present, people will behave in highly predictable ways. And late Cliff Nass famously said that you can take any social psychological phenomena, any theory that you know is well established in human psychology, and be able to show some variation or some version of the same effects in human computer and human robot interactions. And that is a testament to our automatic and thus mindless responses to robots. In 2008, during my time at ATR in Japan, I had the privilege of working with a roboticist named Hiroshi Ishiguro, who famously made a robotic replica of his daughter first, and then of himself next. I wanted to study these automatic responses using this amazing robotic platform. Now, imagine that you're playing a guessing game with a friend. You lay out some objects in front of you, and you ask your friend to pick something that you would guess by asking yes or no questions. What you would commonly see in the scenario are cues that your friend will unintentionally give off with respect to the task at hand. Imagine that your friend is the volunteer on the left, and if you ask them, is what you picked black? He might quickly glance at the object to make sure that he's answering it correctly. It might look something like this. Now, that's very brief, so I'm going to play it again. It's a quick look at the subject of the question. Now, what would happen if I had a robot show these cues? So let's see what that looks like at the very human-like robot first. The robot asks a question, glances at the item, and answers the question. Let's look at it at the less human-like robot on the right. The robot receives the question, glances at the item, and responds. So what we found was that people picked up on this cue on the robot and correctly guessed the item that in the game with fewer questions. So the effect was stronger in the more human-like robots, even though when people were asked about what information they used, they had no recollection of seeing anything on the robot's face or any information that they used. So they automatically responded to these cues in very sophisticated ways. Their performance was affected without any recollection of what information they used. We also respond to such cues in language. There's a large literature on different kinds of cues, like politeness and expertise and things like that. So as an example, our speech are full of cues that indicate our level of knowledge, care, or skill regarding a topic. And the example that I want to talk about, I'll focus on linguistic cues of expertise. When an expert speaks, as opposed to a novice, we see more goodwill toward the listener, references to prior experiences, use of metaphors, and generally their speech is more fluent and better organized. So these are the cues of expertise that we see in humans. Now, what would happen if I made a robot convey the same information with these cues of expertise versus not? Even with very rudimentary toy robots, we see that people pick up on these cues and show more compliance with the robot's suggestions and requests when the robot uses expert speech. Even if the robot has very little knowledge of the topic. And it turns out that this is a highly robust effect to language and culture. We see replication of the same findings across studies and across languages. We did a follow-up study. It was conducted across Wisconsin and Lebanon. And we again see cues of expertise affect people's behavior and the effectiveness of the robot in gaining compliance, both in English and in Arabic. There are a lot of nuances that these studies reveal, but in general, we see this automatic responses to be very robust effects. In 2007, I conducted an ethnography of a hospital delivery robot. An ethnography is an observational study. The robot went around the hospital, controlled doors and elevators, and made deliveries at different units. When it arrived at its destination, the robot made its announcement using human speech. So in this example, we see that human-like cues trigger a mindless reaction, but a negative one. Here, the nurse is talking about how the robot's making an announcement, but there's no one to attend the robot. So if it keeps making that announcement, it's going to kick the robot in the camera. And there are these expectations set by the use of the speech. The cues trigger that, oh, this is a robot that could speak, so it should understand the social situation and not speak when no one's listening. But when the robot is unable to show that behavior, it elicits a very negative mindless response. So we see mindlessness manifest itself in various ways. So let's see where we stand with respect to the mindlessness hypothesis. And I think there's strong evidence that suggests that we apply a human schema to robots and mindlessly respond to appropriate social stimuli. Of course, we see this as a great opportunity. We can tap this human tendency to build technologies that people intuitively interact with. They can automatically know what to do with a robot and automatically respond to them. At the same time, there is a great threat. We can misuse these technologies by over-trusting them. We can automatically respond by buying something that the robot wants us to buy. The cues that trigger mindless responses also set expectations about robots, and they can't always meet these expectations because we expect these expectations are that they behave in a very particular way. I'm very sensitive to those ways. So when these expectations are not met, we can build sort of love-hate relationships with robots. The next hypothesis I'd like to talk about and entertain is that because of their physicality, robots have a stronger sense of presence in their environments than other technologies like computers, software, AI. The robot is present, right? It's right here. It works better because it's right here in my environment. On the other hand, the robot's presence can be recognized as being threatening. All in all, positive or negative, the robot will elicit feelings of presence, which is the next hypothesis. A good example of this effect is a study conducted by our colleagues at Yale University, where a human-like upper torso robot asked people to first complete a simple task, and then asked people to pick up a stack of brand new books from a bookshelf and put them in the trash. The team compared the robot against a video display of the robot and a full-size video display of the robot. In both of these conditions, the robot was not physical. It was on a display. And that was compared to the actual physical robot. What the team saw was that in the simple task, people performed the task in very similar ways across conditions. It didn't matter how the robot was presented to them. But when it came to throwing out perfectly good books, people complied with the requests of the physical robot much more than the visual displays. And to get books, they had to reach next to the robot and pick them up from a shelf. And then with the physical robot, many people went around the robot to kind of respect the robot's space rather than reaching just straight toward the books. In a similar study of human-robot proxemics, and that is the study of distancing between different bodies, between people and computers and people and robots, we asked participants to travel behind a robot to look for something, look for a piece of information that they would use for their task. And we manipulated the robot's gaze behavior, how the robot looked at people. The robot either followed the person by maintaining eye contact, or the robot avoided the person by looking away. And we wanted to see if this effect of presence, of respecting the robot's space and knowing that the robot is there, would be moderated by the robot's gaze behavior. So what you see on the left is when the robot followed the participant. So it's a top view. You'll see the participant moving toward the robot. And what you can see that the participant is maintaining quite a bit of different distance from the robot because the robot is looking toward them. When the robot avoided the person's gaze, looking away, we see that people are much more comfortable with entering into the robot's space and not leaving as much space. So the robot's behavior had an effect on how people responded to the robot's presence. So it's not just about that the robot is physically present, but its behavior affects that presence. It can increase that presence or it can decrease that presence. And when we talk about physical presence of the robot, we're also talking about robots occupying space. And people might see this as a threat or just to find it to be a practical challenge. And this is a photo that I like very much of the Starship robot that we see on our campus, because it shows so many different things. It shows, for example, that robots can take up our spaces, take up this sidewalk that I was planning on walking. And people might be caught off guard and not know what to do, or they might be threatened by that, or walk away, be confused. There are a lot of things that happen in these kinds of situations. And going back to the robot that got kicked in the camera, we saw the robot's presence causing a lot of problems for people, running people over, cornering them in an elevator, just getting in the way, right? People talking about being almost ran over and they were scared. They weren't scared, but they were mad. They got clipped by it and that really hurt. So this physical presence is not just affecting people, psychologically, it's also affecting them physically. So, revisiting the presence hypothesis, I think that there's good evidence that robots elicit feelings of the robot's presence in people, and that this presence has a range of effects on people. People comply with the robot more, take it more seriously, grant the robot more space, and so on. In a sense, we want robots to be present, but it can also come at a cost. The robot's presence can cause conflict or just plain inconvenience. So the next hypothesis I'd like to talk about is that robots follow the metaphor of a human, and that the human metaphor elicits familiarity, and familiarity elicits favorability. So in addition to a hypothesis, I'm proposing a model here of various things that are related to each other. And because of that somewhat multivariate model, I'd like to unpack this a little bit by first explaining what metaphors are. So in design, and I'm talking about any kind of design, whether it's airplanes or software or books or graphics, we often talk about two types of design: idiomatic design and metaphoric design. In language, idioms are speech forms that cannot be deduced from its components. For example, when we say it's raining cats and dogs, we mean that it's raining heavily. When we say biting the bullet, we don't mean biting an actual bullet. And so similarly in design, idiomatic designs refers to design solutions that may not be familiar, but will have to be learned, such as the menu bar on a computer. The menu bar has nothing to do with menus at a restaurant or a bar of soap or chocolate. In contrast, metaphoric design takes a familiar idea from one domain and applies it to another domain. By capitalizing on our familiarity with the idea from the other domain, it jumpstarts our understanding of what we're experiencing in the new domain. So the trash can on the computer is where unused files are thrown away, and we empty the trash can when it's full, right? So the metaphor is followed through its behavior, through its appearance, and in general design. Coming back to robots, similarly, robots follow the metaphor of a human or an animal or another familiar artifact. What you see on the left is a robot called Pepper, made by a Japanese manufacturer, and follows mostly a human-like metaphor. Next one is a robot called Spot, made by Boston Dynamics, and that follows the metaphor of a dog. And the last one is the Starship robots that we see on our campus, which looks like a long-haul truck or a lunar vehicle. So the basis of the relationship between the human metaphor, familiarity, and favorability is a number of social psychological theories, particularly two theories called similarity attraction theory and trait activation theory. I want to talk about them just for a brief moment. Similarity attraction theory suggests that people find those similar traits, those with similar traits, to be attractive. And trait activation theory suggests that human traits are triggered by the presence of trait-relevant cues, which suggests that human-like cues would elicit a human-like response. When we see something that follows the metaphor of a human, and because of our humanity, we respond to that both in human ways, but we also are attracted to that thing. So in the study that I'd like to describe, we wanted to see if similarity in personality would elicit favorability, particularly motivation. So we designed the gaze behaviors of a robot to either communicate introversion as a personality. So what we found is that in general, the literature suggests that if you're introverted, you maintain a small amount of mutual gaze with people. You might see this in people who might look down more, look at their feet when they're talking to people instead of the other person's face. Extroversion, on the other hand, is marked by a larger amount of mutual gaze with other people. So we designed the robots to have low amounts of gaze or high amounts of gaze to indicate introversion or extroversion. What we found was that when the robots express personality match the participant's personality, so a robot that communicated introversion interacted with an introverted participant, people persisted in the task much longer. They were much more motivated. And the same thing happened with the extroverted robot. When the robot was extroverted and people were extroverted, they persisted in the task much longer. So we see that effect here very strongly. This robot has a similar personality to me, and the robot is not actually telling me what their personality is. I'm gleaning that from purely their nonverbal gaze behavior. So you can see how strong these effects are just from very subtle nonverbal cues. We can pick them up, build on them, and act accordingly. Now, this model is very interesting, but the model would suggest that human metaphor would increase familiarity, which would increase favorability or affinity. But it turns out that there are some limitations to this model. And these limitations are best expressed in an effect called the uncanny valley. This effect states that familiarity and affinity will increase as the human likeness of a robot increases. So as a robot becomes more and more human-like, or as I'm looking at a more human-like robot, my affinity or my willingness to engage with this robot will increase. But at some point, there will be a sharp decline. And that's the valley that the theory talks about. Robots fall into that uncanny valley, where you elicit feelings of eagerness or uncanniness. And this effect is also very, very robust. And turns out that with still images, the effect is smaller than alive or moving robots. And this, there are a lot of theories about why this response is elicited. People talk about this giving people a sense of terror or reminding of death, and because at the bottom of the valley, robots look more like corpses. To give you an example, not to show you corpses, of a highly human-like robot that is sort of very convincing in terms of human likeness, but some things are just a bit off, and you can experience the feelings of eeriness or uncanniness in this robot's behavior. This one had audio, but it's not that important that we hear that. You can see that the expressions are not quite right. They are kind of folds in the skin that don't look quite natural, and the mouth moves a little different, and the teeth moves in a different way than the mouth. So we see kind of these cues, very, very subtle cues that from a distance you may not realize, but that kind of throws us off. And that's when robots fall into that valley and elicit this feelings of eeriness. So let's see where we stand with respect to the metaphor hypothesis. I think there's good evidence that familiar metaphors elicit a sense of familiarity with the robot, and that familiarity results in some sort of favorability. We like robots that are like us, and we respond to them in predictable ways when the right cues and traits are present. However, there are limits to this effect. So when we have expectations of how this metaphor should be followed, we like robots that are inspired by humans, in that scale. Think about the first half of the scale. We want human-like robots, we want human-like traits, we like them. But we respond negatively when those qualities, human-like traits, are violated. And that's when we start observing that valley effect. The last hypothesis that I'd like to discuss is the discovery hypothesis. And this is the suggestion that we're interested in robots because they help us discover what it means to be human. Robots are almost a medium for exploration, understanding, and discovery. By building them, by interacting with them, by thinking about robots, we think about our humanity and what it means to be human, what it means to be alive. And this exercise is very important to us. The Nobel Prize-winning physicist Richard Feynman had the following quote written on his blackboard at the time of his death in 1988. He said, "What I cannot create, I do not understand." I mentioned this quote to students a few times, and I joked that this is as close as I can get to collaborating with a Nobel Prize winner. People interpret this quote in many ways, but to me, Feynman is saying that trying to build something, understanding its principles and constructing it is a way of understanding it. In a way, we're building robots and we're building them to be human-like, really to understand ourselves, understand what it means to be human. Sherry Turkle, a psychologist from MIT who has studied the societal effects of technology since the 80s, had talked about computers and robots as the evocative object. Just like what Feynman said, she argued that building computers and robots and simulating basic mechanisms like memory, processing, interaction, we built at least a simple understanding of ourselves. Turkle also studied how children and seniors formed relationships with robots and described interactions with robots as a form of a Rorschach test. Robots as evocative objects provoke reflection on what it means to be alive, to be human, or to be a person. We see this very much in the example of a robot placed in a shopping mall in Japan, where the researchers saw an unusual level of abuse directed at the robot. Children would tease, hit, test the robot, and generally show abusive behavior toward it. They would get together and bully the robot, shove it around, change its course, and just nasty stuff. Turkle argued that such behaviors would indicate problems children might be experiencing at home, or just generally signal how children would behave with other sort of lesser beings that they can exert controlled power over. And I think that's the first Rorschach test about this example, that children behave this way toward robots. And we only understand and know about this by placing this robot into the human environment. Robot. The second one is the second challenge, or the second Rorschach test, is how can you actually stop this? Which brings us to an engineering problem. Can you actually engineer a solution to stop abuse? The colleagues at ATR in Japan found that the most effective way of stopping abuse was to change the robot's trajectory when abuse was detected and travel closer to the nearest parent for intervention. So what you're seeing is that the system is calculating a probability of abuse at any given time. A child approaches the robot and probability goes up. If the child spends more time, goes even higher. And if multiple children come together, the probabilities jump up. And at that point, the robot decides to take action and identify a parent, maybe modeled, well, this child came with that parent, so I better walk toward that parent to stop this abuse. In 2014, we conducted an ethnography of collaborative robots placed in factory environments. These are robots placed on production lines alongside people. And there's quite a bit of interaction between human workers and the robot, both in the form of people monitoring the robot's work, but also passing things to and from the robot. So there's sort of like line workers that you're interacting with regularly. In our naivete, we expected to see perhaps coordination issues and workarounds that people developed and generally kind of emergent collaborative behavior and issues. What we found was a profound expectation of sociability in the robot. We found, for example, that production lines are extremely social environments where people's hands are busy, but they continuously interact socially. So people expected the robot to participate in the social environment. They wanted the robot to greet them, ask about their day, shoot the breeze. And placing the robot in this environment is, again, a Rorschach test that reveals something about us, about our expectations. Where do you want to see sociability? Where do I expect social interaction? So let's revisit our last hypothesis. When we introduce robots to human environments, we learn more about human behavior than designing robots. We construct these behaviors in robots. That's one way of learning about human behaviors because robots have to display these behaviors. And secondly, by studying how people respond to these robots. So I presented 5 hypotheses on why we care so much about robots, what makes them interesting, what makes them special. In general, I think there's good support for all these hypotheses with some limitations. And in doing this analysis myself, I found that these hypotheses are not necessarily mutually exclusive. And my list first started with 8 hypotheses, and I consolidated them to 5. But then there are deeper connections among them. So I want to conclude with maybe a meta-hypothesis that brings these together. And perhaps a good way to summarize my conclusions is that there's a possibility of a meta-hypothesis that we want our environments, our culture, our artifacts, the artifacts that we interact with, to somehow reflect us and reflect our humanity. We want to make technologies in our image, and this makes them more familiar and more predictable. And by building technologies in our image, we learn about ourselves and we learn about what it means to be human. With that, I'd like to thank you again for your attention, for coming here on Valentine's Day. I'll be happy to answer any questions you might have.
Just a reminder to just
Microphone in the
walk up to the
middle,
microphone.
yes.
Thanks.
How has your work changed over time as AI and processing power has increased?
Yeah, great question. So the question is, how did your work change over time as AI and processing power has increased? I would say, when I first started my faculty job, we would look for ways of faking robots. We would say, okay, one day this robot will work in the way that I want it to work, but there's no way it's going to do that now. We call that the Wizard of Oz method. Okay, there's an operator behind a screen moving the robot in ways that we want it to move, but people are not aware of it. That's what we used to do. Because we knew one day those capabilities will be in place, but it wasn't there yet, but we still had to do the research. I'm happy to report that that's no longer the case. We built robots that autonomously work. And I remember this comment that my PhD advisor said. She said, you can fake robots, but when you actually face the challenge of building the robot as intended to be built, you may not make the same design decisions, right? You make simplifications, you might choose different methods of interaction. So what you're learning when you fake versus what it ends up being might not match. And I took that to heart, and over time, what we started seeing, and also my field started seeing, is capabilities have increased. When 13 years ago, detecting a person in an image was a challenge. Doing it reliably was an extremely hard challenge. Doing it in a way that people are moving, you're identifying who they are. These are trivial capabilities that come pre-installed in a robot that we use as a research platform today. So the capabilities of basic capabilities have really expanded. Now we can actually look at much more in-situ interactions that can happen in the wild, can happen more spontaneously. So we can really kind of focus on the design challenges, on the understanding of what's going on in human-robot interactions, rather than focusing on, faking that the robot works in a particular way. And I expect that, as the faster kind of accelerated growth in AI, we're going to see more of that happening, especially as systems are able to construct language in meaningful ways and use kind of sophisticated models to hold conversations. Things are going to become much more sophisticated in research as well. Thank you for the question. You want to come here?
Good evening. About the abusive behavior of those children and your other hypotheses, how are they changed by the culture that these experiments are performed in?
It's a very good question. So I would say that, cross-cultural studies are very rare. And some of it is historical. So for example, trying to put a robot in a shopping mall where the robot can freely go around, potentially harm people and things like that, can be very hard in different countries. That study was done in Japan that they were able to do it in Japan. That's one of the reasons why it's very hard to make actual comparisons. But I think in general, what we see is that there are two types of similarities and differences. There's certain things that work the same way across cultures, like the effect that I talked about. If you have cues of expertise in the speech I'm hearing, I'm going to treat that speaker as an expert, and I'm going to respond appropriately. So we saw that across cultures, for example. Other things, we see it very differently. In fact, seeing that video from a Japanese mall is actually even more shocking to me, because I've been in Japan, and generally in public there's a lot of respect that people pay each other. So I think there are certain cultural norms that are very, very different across cultures, and we don't know exactly what those are because the studies are not in place. And I think the best way to really gain that knowledge is the discovery approach, where we introduce robots, we see what happens, we understand what happens, we build knowledge around that and start kind of expanding that across cultures and see what happens. Yeah, thank you for the question.
So my question is how did you get into robotics? Like, how did you get into robotics in the first place?
Yeah, good question. So I was actually trained as a product designer. So I went to study product design, and I went to industry to work designing household appliances. And this was in the late 90s, where there was a growth in this idea of an intelligent product, or a smart product, or a smart home. And at the time, reflecting on that, seeing that kind of interest growing, I realized that if we're interacting with our environments, with our world, with our homes, with our cars, and they are smart and intelligent, we won't be interacting with the buttons and dials that we're traditionally interacting with. We're going to be interacting with the intelligence, and we might be talking to them. We might be understanding what the system is doing. And I realized that my training was not sufficient for that as a designer. So that made me want to go back to grad school, and I landed at Carnegie Mellon University, where you see a lot of robotics infused in a lot of things, and I think that was quite a bit of luck to see that. But I think this is a reflection, at least what I ended up doing is a reflection of how traditionally we have adopted, we've engineered, and we've introduced technologies into society is also shifting because of connections, the internet, artificial intelligence. The way that we interact with these things is definitely changing, but also the way that people will do the research and people who will do the engineering will also be changing. So that's sort of my convoluted path into it. But I think thinking about robots and intelligence, artificial intelligence, as kind of the locus of interaction people will have with technology, as sort of our interface with technology, really brings our attention to that intelligence rather than buttons and dials that we traditionally designed. Thanks for the question.
One online question, then we can get to you. Why do you think we often portray human-like robots as threats in film, whereas in-person interactions and some of these examples that you've shown have been pretty positive?
Great. Yeah, great question. So, I think at some point I wrote this paper where I was studying film plots and narratives. And one of the interesting things I learned is that a lot of movies and film and scripts follow a very similar structure. And there's always some kind of disaster or some kind of strife that people have to go through. And robots really make a good source for that. So I think for movies to be successful and follow that plot, robots sort of have to be the evil one. In the real world, most people work in robotics are researchers like myself, or people want to sell robots as products. It's a very hard argument to make that this robot will kill you and you should buy it, right? So I think you see that mismatch between the creators of these technologies for human use, which is very human-centered, and portrayals in entertainment, which is very different. And that's sort of what sells and gains interest in that field. So I would say that that's the difference. But I would also say that there's definitely a lot of crossover between fiction and science. Often science is informed by fiction or inspired by fiction, and fiction is informed by science. A lot of movie crews will actually hire scientist experts to make sure that their science is right. And then often scientists will say that, oh, I was inspired by this movie, right? The Jetsons, I was inspired by that. That's why I'm working in robotics. So there's also that. Thank you for the question.
So what kind of robot would you like to have in your own life, like at your office or at your home?
Yeah, that's a good question. I think that as I use more technologies myself, I'm finding a lot of the interactions to be somewhat tiring, right? So a lot of things I do, I don't have to verbalize them, right? I go, wake up, make a cup of coffee, and do the dishes and sit down, read something, whatever it is. I go and do them. Now imagine an intelligent system in your house that's going to help you with that. So you wake up and you say, make the coffee, do the dishes, and you turn on the TV. That's a lot of instruction. So I think what I'd like to do is to have systems and robots that kind of do these things in the background, understand our patterns, and really kind of seamlessly do all these things, right? Well, that if I'm coming down the stairs, the coffee machine should turn on, right? And yada, yada, right? So understanding these patterns and really adapting to them. And I think it's really sort of the more of the future. But you see where we are with technology, right? Alexa, do this, right? Explicitly have to say things. We used to press buttons for everything, just like that we have to say everything now. And I think down the road, we're going to see our intent being recognized immediately, patterns are modeled, and things just kind of seamlessly adapting to our patterns. And that's sort of the future that I'm looking for. Hopefully I'll get there by retirement age.
So with artificial intelligence, people talk a lot about that. And one of the hot button issues is it sentient? Will it become sentient? Should it become sentient?
Yeah.
Very strong feelings a lot of us have, or desires or fears.
Yeah.
So from your angle in the robotics, I mean, it's a particular angle in this,
Yeah.
and this thesis you presented today. There's connections. Do you have any comments?
Yeah, that's a great question. So I have the fortune of coming from a product design background, which is very human-centered. So all I care about is that the robots benefit people. From that angle, does the robot have to be sentient in order to do that? My current approach is not necessarily. So as long as the robot does what it's supposed to do, I'm okay with that. Now, if you look at the field of robotics, there are different strains of thought. So in the 60s, Rod Brooks, famous roboticist, came up with the notion called behavioral robotics. So rather than targeting these robots who would know it all, sentient and feelings, and really models your feelings, he said, why don't we just say, make the robot do just one thing, just focus on the task. As long as it does that thing, that's all that we care about, right? Maybe the robot has to make sure that it's charged so it doesn't die on you. And then on top of that, it does the things that you want it to do. That's all it does. So that is the inventor of the Roomba robot, right? What does the Roomba do? It charges itself, goes vacuums, comes back. No, no intelligence beyond that. So it's very simple, really focusing on the benefit that the robot is providing with some very basic mechanisms for sustaining itself. So that's my current feeling of, I don't necessarily want to see sentience or anything like that. I'm more focused on what do we need to build to benefit people? Yeah, thank you for the question.
So I think this may be the last question. It's
Great.
one of the online questions. You had your hypothesis and some interesting findings, but out of those, what have you learned that has really surprised you?
Surprised me. Out of the hypothesis or out of the research? One of the two. Okay. Interesting. Yeah, that's a. So I would say that looking back at it, it's not analyzing these. It's not a lot of a surprise because it all makes sense at the end. But at the time, I would say that some things are very interesting. I would say that seeing these mindlessness effects are very shocking because, I showed you a series of studies, just pick some examples, but there are some examples where the cues and the behaviors are so subtle that they're almost not discernible, but you still see people responding to those extremely fine cues. So I would say that, seeing how sensitive we are toward things of humanity, things of being people, how we behave, how we expect other people behave, it was really a shocking experience, I think, seeing those. The second thing I would say is that example of, the robots, people expecting the robots to be social at the factory line. I realized that there was a lot of, assumptions that we were making about what certain environments are like. And I think, again, humans are really surprising us in that sense that, they expected a lot of sociability, which is not something that we expected. Thank you for the question. So time for one more? Okay, great.
Have it happened for you to watch a movie Wall-E?
Yes,
You saw
I have seen it. I've seen it with my kids too.
Reproduce the facial expressions of those robots and one that you built because they kind of very, very emotional and lively one in the movie.
Yeah. Is the question?
Do you find those facial expressions very very emotional, and do you plan to introduce them in robots that you?
Yeah, it's a good question. So WALL-E as a movie is an animation. So one of the things that happen in that movie is that the robot stretches and squeezes and changes its form to express more than what a physical robot can do. Okay, so there are some tricks that are in the sleeves of animation experts that can make that happen. However, it's actually an active area of research to bring some of those principles into physical robots. So for example, we put a breathing movement on a collaborative robot. So the robot doesn't just stay still when it's idle, kind of moves around a little bit. It looks like it's breathing. And we found that people just responded very positively to it. They know that the robot is on, it's not broken. They know that the robot is somehow idle, maybe listening. It just feels like another biological entity, right? So people were much more comfortable with this robot that had sort of like small noisy motions rather than stiff waiting. So the kinds of things that you talked about has a lot of promise for robotics and for technology in general. So there's some sort of excitement ahead of us where we'll see robots to be much more expressive in that sense. Yeah. Thank you for the question.
Thank you very much. And thank you everybody for joining us. And I'm going to end it with a little surprise of my own involving some of the themes that you talked about. So last week I was walking through campus during that very heavy snowstorm that we had. And I encountered one of those little Starship robots, and it had slid off the sidewalk and it was stuck on a snowbank and it was trying to unstick itself. And it was the saddest thing I ever saw. I almost cried. You know? And I was amazed at the emotion that was evoked by that little machine struggling to get itself free.
great.
So this was really, really interesting. Thank you very much. And thank you all for joining us.
Thank you for your attention.